sort not using comparables. So we'll just take a look at that and do it side by side with the one that does use comparable. You'll see that the sorting algorithm is really not different at all. The only thing is that it passes an array of integers to it. It doesn't use comparables. The big difference is you don't have to use the entire program because you don't have to implement the comparable interface. So we'll take a look at that for the comparison.
Okay.
Okay, so just to refresh our
You're gonna need a new file called
memory.
input research
This is the way.
Okay.
input research except in demo.
Oh, sorry about that.
I don't think so.
Yeah.
Like this, right?
Yeah, unless you just change the name.
Okay, so the regular program, it has an array of something from the contact class, which we still have to use. So, it's an array of contact objects, and then the array is called friends, so 0 through 7, and then the array friends is passed to selection sort down here. Okay, so the thing we're going to look at is that how would this work if we don't use the comparable interface? We look here and we don't see any evidence of the comparable interface yet. So we look up top, is this implementing comparable? This one isn't. So then we can look at the contact class. So we've got contact class here, and so this one implements comparable. So we notice that in this one, from yesterday, we saw that we have to have the compare to if you implement the comparable. So now, let's take a look at one that will not implement comparable. So the original sorting class has as its parameter list, it accepts an array of comparable data types. So it says comparable and then open brackets. And then notice that it also says comparable temp. That's because you need to use a comparable, compatible integer that's going to store each of the values during the swap. So comparable is for the integer inside the body of the program, and then comparable with the array brackets is to accept the contact array that's going to be passed. So that's what we saw yesterday. So let's take a look. So now here is the sorting that I rewrote, giving it just a different name for the class, and then notice it doesn't accept a comparable array; it accepts an integer array.
It's not an array.
So that's the difference there. And then notice instead of comparable temp, it says int temp. So where it says comparable temp, it's actually making an open-ended variable type. If you notice brackets back down.
String operator.
Notice that it doesn't give a data type.
You can put it
That sort of leaves it
on the
open
driver
to you, so you can sort of use it open-ended.
string operator.
Let's not focus on that aspect yet.
Is that T the default thing that you have to put in when you're using comparable?
Well, you can specify that you wanted to accept only strings or only insert, but if you just leave T in there, you can pass it anything. So I never see a reason to restrict it. And it's not that way, so you can. So this will make. So this temp will be able to hold an integer scalar variable. This is a comparable, but with the array brackets after it will accept an array. So now this is the one with comparable, and here's the one that I rewrote. So it accepts just an integer array, and then it has just an integer regular that's temp. All the rest of the program is the same. I believe all the rest is exactly the same. So the only part that is sort of different is down here, but I didn't do insertion sort for it. It was just selection sort. So for selection sort, the only two lines changed are the parameter list and this. So there we go. So insertion sort isn't included though. It's just selection sort rewritten. So those two things make this a regular selection sort. So you pass in an array, and then, as we said yesterday, the first element in the array is set to min, and then the list is scanned one by one, and then it will sort your array of integers. So this one is not polymorphic, because it will only accept an array of integers. But if you made an overloaded selection sort method with accepting an array of integers, an array of doubles, an array of, if you did like 6 or 7 selection sort method overloads, then you would have something that is polymorphic without using comparable. But this will work exactly the same. Only difference is the fact that we are not sending in something that is directly comparable. However, you notice that it does sort everything correct. So let's just show that it does that. So I also rewrote a driver class, so that we'll see how simplified it can look. So we have our array of integers, and then we call the rewritten selection sort, and then we print out the array. So we pass in 67, 8, 76, etc. So we should see it properly sorted after we pass in that array. Here, take a look. So that array is going to pass in right there. Which one of these? And we see that it did work correctly. So if you change this data type to anything else, all you have to do is change the parameter list and the temp variable to that kind, and it would also work. You can also make an array of doubles, an array of longs, anything you like, as long as you overload the constructors for the method in the rewritten version that I did. However, it is worth your time to understand the comparable class, because it does allow you to do kind of anything you want. And since I was at office hours and I didn't have anything to do at the moment, I came up with an idea for a little side project for myself, and I'll post it up so you can see it, and if you want to extend it, you can. I was wondering, how would the comparable class work? Because behind the scenes there has to be something else, because if you look at the documentation for comparable, all it is an interface that has one method, but it accepts all these different data types. So I was wondering, how hard would it be to make up a class that you can just pass any data you want to, and it will identify what the data is. So I think I got I'll show you what it looks like, and then I'll post it up to Blackboard in case you want to continue along with it, or at least see it. So I don't know if I'll keep calling it object acceptor, but I called it that now. So where it would say comparable before, that's where you can pass it anything. So I essentially allowed it to work with the object class, which, as we know, everything in Java is an object. So if you pass an array of strings to object, it will allow it. But then you have to identify it as an array of strings. So say that you pass an integer as an integer wrapped integer object. So you pass it here, and then there's a method in Java, instance of, if the object A is an instance of the integer class, then assign A, cast it to an integer, to the global variable that is an integer type, so that you can get the number part out. Same thing with the string. If A is passed in as a string, so you can pass an integer as a string. If A is an instance of a string, then assign A to the string variable. And then each time there's a variable called meter that will tell this class which one has been passed in. If meter is 2, then the 2 string knows that a string has been passed in. Because your 2 string then has to always work for whatever data you want to print out. So if the 2 is the value for meter, then you know that it was a string that was passed in, and then you can just print out the string. So I only got it done for 2 data types so far. I thought I had one more, but I didn't do the 2 string part. So here's where we have an example of the polymorphism of comparable array. If A is an instance of contact 2, so I made up I just took contact 2 and copied it. So if A is an array of contact 2 objects, then I just tested it to see if it would actually allow it to print out the first element, and it does, so it works. I was wondering if it was even going to work, because it said that you can only use object and instance of for Java-derived objects, but it worked still. So even though contact 2 is a custom class, it still worked. Oh, and the reason I also got to this is I didn't sit down and decide to do this, but I've been trying to get a copy of the original Java specification that was written by James Gosling and Bill Joy in 1996. So this I'll post up when I post that too, but it's just for your own reading. But I got like a couple hundred pages into skimming it. I got past this, right? That's fine with methods. So it's like 800 pages long, but it's the original entire Java specification when it was written in 1996. So the original authors on it, which is, so James Gosling is the guy that gets most credit because I guess he's first on the list. Bill Joy is probably actually more fundamental to computers because he wrote the TCP/IP stack. He wrote a lot of Unix. He wrote just a bunch of things, but he is not as well known for his Java stuff, and he is part of the Java spec. Guy Steele, I don't know much about. I'll have to look him up sometime. But those are the 3 original authors, and it gives you all the history of it. Java was originally called Oak, the Oak tree for whatever reason. Then it was renamed Green, I think, and then Java finally. So it gives you the entire first specification. You can see all the things that were not in it back then. Scanners didn't come in until like 2005, so there are lots of things that you might notice are not in it. You have to just give it a pass through. But that's how I found this instance of thing, because I wanted to see if you could identify a class before you told the program what it was. So that's one way. There's also another one that's called getClass, but it returns you back class space and then the type and then the name of the class, which isn't as easy to use. So that one sort of worked, but you have to do an instance up for every kind of thing that you pass in. So I want to see if I can make it polymorphic just on a one-shot client.
Do we do it specifically to be able to sort 2 arrays of different types, or not specifically?
I just wanted to see if I could rewrite the comparable class myself.
Okay.
But I haven't, that's not there yet. Because comparable, you can pass it anything. Like this, you can pass anything, but because object will accept anything. But you need to identify what it is. Because if you just say object, print it. If you pass object string, then that'll be fine. But if object is a contact 2 array, it doesn't know how to print out anything there because there is no built-in 2 string for it. So I'll see. But I'll post it up in case you want to check it out. That's like kind of whatever grabs your fancy. Just try it, start programming, and you'll see it's not as involved as you think. Although it's a little slow going, but programs are slow going. Nobody writes 1,000 lines of code. It's a few lines here and there, and then you get things finished. Okay. Oh yeah. So the other contact 2 class that I made was simply something that had a copy of the content class. And I didn't have it implement comparable because I was reconstructing comparable, so this one just passes in the same stuff, but without implementing comparable interface. So let's go and take a look again at where we were with. So I think we did this. So we did this. So let's look at the insertion sort and then binary search. I didn't add in the recursive binary search yet. We'll do that as like third thing. I figured I would leave it the way it was in the lecture so that we do it just for the iteration and then we'll do the recursive binary search. Okay, so right now we have already done using the version that does comparable. We did selection sort, so now we'll do insertion sort. So remember, the big difference is going to be that each round through checking whether or not the thing that's in the current position to be checked is going to be moved. Several things will be moved per round instead of just 2 swaps happening. So to give the example similar to what's in the book or in the slides, 3, 9, 7, 2. Okay, so when insertion sort starts, it's going. I want to see the example start with the first time. Okay, so start out with 3, and then remember that you're comparing the thing to the element that is to the right of what you're checking out. So 3 compared to 9, 3 is already sorted. So 3 is it's sorted already. So then you go to 9, and then let's compare this to the one that's in the example because it will be different because we have 3, 9, 7. Let's see how that's going to be different with the one that's in the example. Oh no, it is the same, just the same. So the one in the example, it starts out with a 3. So 3 is already sorted. So 9 is said to be inserted again, which I believe that it is in the code. You can always put a print statement in to do it, but I believe that it is re-inserted and it's just re-entered into that place. So then 9 is compared to the one that's on the right. So 9 compared to 6, 9 is bigger than 6, so 6 is going to be more. So 9 compared to 7, 9 is bigger than 7, so 9 is going to be more. So we'll look at that. Let's just move this back to our. Okay, so 9 is larger than 7, so 9 and 7 are going to swap places. So 7, 9, 2. Okay, so then 9 compared to 2. 2 is, let's see, is this what's going to happen with this direct round?
9 is bigger than 2, then 9 is small.
Yeah, but I think for this round, that's the biggest thing that's going to happen, at least for this round of swaps. Meaning, if 9 had been swapped with, like when we do this, there's going to be more. So right now, for that round, this is so 9 has been moved, and now for the next round, we check 9 against. Let me just make sure I'm saying this right. Insertion sort is not as easy as selection sort to think about. So 9 compared compared to 2. Let me just verify if this is right. So, you don't get it fed into your head the wrong way. Okay, right. So in the graphic, it's not immediately obvious like what's happening during the round that you're looking at. So yeah, this will move each round. So 3, 7, and 9 are sorted. So now we have to insert 2. So 2 is going to move to here, move to there, move to there, and then move to here. So 2 has actually 1, 2, 3 moves. So notice that there's a bunch more swaps happening per round. So first round, nothing happened, and then 9 and 7 switch places, but then 2 also need to be sorted. So 2 move there, there, there. So 2, 3, 7, 9, and then this is the here. So that will happen during the round that 9 has been moved with 7. So we have 2, 3, 7, 9. So now 8 has to be sorted. So 8 simply moves to that place, 2, 3, 7, 8, 9. So insertion sort is different than selection sort, where you have more moves happening per swap. Per swap meaning the first is a for loop and then the second is a while loop. So you have the for, start scanning through, but then it says while there is an element that needs to be resorted, to keep resorting. Whereas if this was selection sort would have done 3, and then is there a number in the list that is less than 3? It would have been 2, 9, 7, 3, 8. So that would have been the first round for selection sort. So it's a different pathway of getting there, but you get the same answer. And since insertion sort has one loop and then another loop nested inside, they're still both n squared, meaning O n squared, but there does tend to be more swaps per round for insertion sort, but then there's probably less rounds than selection sort, so it evens out in the end, but they're both considered n squared because there's a loop inside of it.
Do I understand correctly that the number of rounds is the for loop, and the while loop is the number of swaps per round?
Well, the while loop is, just consider 2 loops, like a for, and then there's a for loop nested inside of it. One is n and the other one is also n. So you would just say it's n times n. Whether or not this nested one does 7n, then it would just be 7n squared. So n squared and 7n squared are both considered n squared. So if the middle one has 7 squares and it happens, it doesn't change how you categorize it.
Yeah, but I'm not specifically about the responsibility of each loop.
Of what?
The responsibility of each loop. The task each loop does.
The top loop simply shifts to the next position in the list. So when you go from, you look at 3 compared to 9, they're already sorted because 9 is greater than 3. So then 9 is compared to 7. When you shift, so 3 is compared to 9, that's what the first for loop does. It shifts along the array to start doing the checks. So 3 compared to 9 is already sorted, so 9 compared to 7, then 7 has to be swapped over. So as it advances forward, that's what this does. But then while position is greater than 0, meaning, so it's position, so notice that this says position minus minus. So position equals index is, so it's position equals index, and then we have to, so key compared to position. Okay, so key is, so this is basically saying, until you're at the end of the array, and while position is greater than 0, we will have to do a print statement for this because it's not jumping in my head exactly what that would say. Position greater than 0 is compared to. Let's just do a print statement so we can see. I'm just going to put a print statement here that prints out the value of position and this. So we can just tell what it means and we'll be able
What
to.
exactly do we compare in this case?
Pardon?
We compared key. What is key?
T is basically just saying that we haven't declared what type of
I mean
what type
key.
of data
Key.
type. Yeah, right here.
No. The key. Key.
Oh, key.
Yeah.
So key is this. So key is another integer, just like we had up there where we had comparable temp, and then the temp stored the value of an array. So this is the an array value. The list index is going to start out at
The numbers of the array, right?
yes, the index in the array.
So basically, what can I come up for a second?
Yeah.
So what this does is just compare the previous element to the next one. Or
Well, that's what I want to look at because I don't want to guess. So what
Okay.
it's like see and then we can evaluate what it's.
but basically, this is the compare of elements happens here, right?
Well, yes, because notice that this part is only shifting the array forward, but it's the same thing that we have with selection sort. Selection sort, all the stuff that when the swapping happens is the outer loop. So the outer loop is simply to advance forward in the array. So the outer loop is like, if the array was like a set of places, you hop one place for the outer for loop, and then the inner for loop does the swapping action, and then you hop another place to do the check, and then when you're finally at the end, it's if the algorithms work correctly, then it's correctly sorted. So let's put a print statement for printing out position and this. So right now this is a Boolean. So let's print out these three values. Let's print out position, t, and this position minus 1.
Let's see.
The only thing I want to make sure is that by typing in this position minus 1 here, I don't want it to increment by accident. Let's run it and find out. Because sometimes when you write something in, it will actually do the thing that you're writing in instead of just printing it. So we'll know if we take that right, whether or not. So we're printing out Q, we're printing out this. I'm going to put in a string for that. This. So let's see about those values. Let's do a nice line break between them. So let's see. So now we go back to our phone list and we call the other sorting algorithm. We'll call insertions. So, let's see what it did. It did something. We got possession. I think it gave us the information we wanted, but what we have to do is we have to recategorize one with a capital B so that we are getting the intermediate back. Remember we did, oh, maybe I didn't do it with you guys. Maybe I did it with the second class. So by changing B to a lowercase b, lowercase has, is a higher value than uppercase. Yes, lowercase values in the ASCII table have higher ASCII values. So a lowercase b will be categorized as if it is higher than even an S, because S ends at like 97 in the ASCII table. Lowercase b is after 97, so it gets sorted ahead of it erroneously. So you have to watch out for capitalization if you don't use a 2 upper or 2 lower. That was what was being demonstrated. Okay, so it's properly sorted, so it worked right. Now let's see what it tells us. Okay, so position 1, and then key bonds Sarah. This position is so let's do another line break after this position. Okay, so we got so with the original list set up where it was Smith, Barnes, Riley, yes. So position 1, Sarah Barnes. List position 1. Did it? What am I gonna do? I gotta put a line break after the data for list position 1 also, because it's not clear what's being there. And I want to put a line break here. So let's say plus. So now that's much more clear. So position 1, and then the T is Barnes Sarah. Position -1 is Smith John. So now position 2, Mark Riley, T Mark Riley. List position 1, Smith John. Okay, so let's see what the next one is. So it was Barnes Sarah, and then John Smith was the second one. So it's like Barnes Sarah, John Smith, and then Riley, and then Smith John. So the Riley and Smith are being sorted at that point. Barnes moves to the first part, and then Smith is still at the second part, so then Riley is moved to where Smith is. So Barnes gets to the 0 position, Smith is at the second one, so then Riley is compared to Smith, and then Riley moves to where Smith is. So it's going. Originally, Smith is in the first place, Barnes moves there, Smith is now second, and then Riley and Smith are. So that's what we're seeing there. So you can see where, looking at the print statement of the stages of progress, it's a little bit helpful. So then we should be seeing more gets in the next evaluation. So let's see. So position 3, Laura gets and then this position -1, John Smith. So we had Barnes go to the first one, and then Riley and Smith swapped, so it's Barnes, Riley, Smith. And then Getz is going to be compared to all of them, and we know that Getz is going to be before Riley and Smith, but not before Barnes. So Getz is going to be made to place right after Barnes. So we got Getz. Let's see if we can look at all of those. And we'll only shrink the text and concept. It's going to be hard to see this. Maybe we can print the array trap. Like go here. So let me comment that out. And maybe if every round we print out the array. Figure that out. Let's see. So the array is printed out back in the driver program this way. We just have to call it a different way. So even though it's n squared, we're going to be making it n cubed just because we're going to have 300 loops, but this isn't really part of the original, so it's just kind of for us to look at it. Step together with that stuff. So let's put the printout of the array here. Shrink it. So the array name is list. So we print out. Let's see if we go to look at the list of array. We got a list. So we have so hopefully none of the curly braces jumped in when I pasted that in. So every round before anything happens, we'll try to print the array out so that we can see the array progress and see if it looks like we would expect it to based upon the example just using integers. If we assign, so we got Barnes would be just arbitrary values. We don't have to use real ASCII values. B would be 1. And then we have, just so we know where they're going to be in the order again. So in the original program, we have a B, we have, the next one would be 2 G's, so GE would be the second one, and then Guzman would be the third one, GE would be the third one, and then, oh, there's a grant too, R, D, so that would be grant. And so 4 would be GU, and then Riley, and then the 2, then Phelps. So PH, 5, and then Smith, Larry, Smith, John would be first. So Smith, J, 6, Smith, Larry would be next, and then I forget Riley. I think I forgot Riley. So we'll just change these to 7, and then Riley will be 6. So this will be the ordering in the end. So if it starts out as S, B, R, G, S, PH, etc. Let's see if if each round goes along as if they were numbers. So when it first starts out, the array is going to look like, I'll put it like right here. So the array is going to start out as 7, and these numbers remember, they're just relative to each other because they're all capital letters. So it'll start out as 7, and then Barnes is going to be 1, and then Riley is going to be, hopefully I'll get this right, 6, and then Getz will be 2, and then Smith Larry will be 8, and then Getz so Riley, so Smith, Barnes, Riley, Getz, Smith, Larry, and then Phelps will be 5, and then Guzman will be 4. That's, and then Krantz will be. So the ordering of the original array will be 7, 1, 6, 2, 8, 5, 4, 3, where 7 means John Smith. So if we see John Smith first, and we see Sarah Barnes listed as second position in the original array, then we'll know that we're seeing the original array. So we can see it each round as it progresses. And if not, I'll have to print it outside the form completely first, and then we'll have to print it inside the form. But I don't think it's changed the place where I commented out the other one. It wasn't as helpful. So it looks like it's doing what we want, but we need to at least put a line break in so we can understand what it's doing. So let's simply put slash n, slash n, then slash n, this. Okay, so when we're looking at, when we see the one that it's just us printing out the list again, we'll see slash n, we'll see list, and then the array, and then n list. And we know that those are just the iterations of it being printed out each round. And when we see it finally, that will be the sorted version. So let me just grab the list and print it in Notepad so we can take a look at it when we see the first one printed out. That's, this, this. Still. Okay, so in the beginning we have I guess we don't want to put that. We want to put it after. We want to put the end message last in the minutes. So we'll print out the list, and then we'll see on the list where it actually finishes the list. So, see if that's working. Okay, so when it first starts out, we have Smith, John, Warren, Sarah, Riley, Mark. So the original list, let's just take a look at it and see if it matches. Smith, Barnes, Riley, Getz, Smith, Phelps, Guzman, Rand. Let's see if that is the first list. It is. We look over here, and we see that that is indeed it. So the first round through, everything is the way it is when it's passed in. Smith, Barnes, Riley, etc. So that's the first round. Then it says end list, where Grant is the last one, so it's unsorted. So now when we do the second one, we'll be able to look at it and just get rid of all this stuff over here. So we'll just use this as a reference. So remember that one is for B. But I think printing out the arrange more helpful. Okay, so that was the first round. So now second round, you notice that Barnes, Sarah has now been sorted with John Smith. So they've been swapped around. And then Riley Mark is going to swap with Smith, so it's going to be Barnes, Riley Smith, and then Getz is going to swap with both of them. So this to this is going to be one swap, and then Riley and Smith is going to be another one swap, and then Getz is going to swap there. So that'll be two at once. So let's take a look at the next round and see what happens with Getz relative to. And the next round actually will be Riley and Smith. Let's see what happens the next round. So this is the end of this round. All the rest is still unsorted. So now next round we have Barnes, Riley, Smith, and now this will be the next operation. So Getz should go here then, like it should. I'm hoping it'll work out the way that we expected, because I think the print statement will allow that capture. Because the inner one, well, we'll see. Because the inner loop, I don't know if we'll have to put it at the beginning or the end. So if we don't see that happen, I'll have to move what we print out. Right? So this is the next one. So first, Barnes and Smith moved, and then Riley moved to where Smith was, and now we're going to be looking at how Getz moves to those beginning three. So it did do it that way. So notice that Getz was here. So Getz moved to where Smith was, and then Getz moved ahead of Riley, two at once. So the first two were just one move positions, and then the next round was a two move position. So that's how an example of where insertion sort is different than selection sort. Selection sort will do one swap at a time, meaning one swap per two for loop progressions. Insertion sort will do one or more or zero. If it's sorted already, we're ready. But if it needs to move two places, so Getz, remember, was going to be here. So we'll just look at the last one, and we'll use this as our example of seeing how this works. So we can see that, so Getz was here, Smith and Riley are there, so Getz is going to move to where Smith is, Smith will move ahead. But then Getz also needs to move ahead of Riley, so that's where we go 1, 2. So that's the inner line. So it goes, so Getz being here, moves there, and now Getz is sorted. So then we look at the next one. John and Larry Smith are already sorted. So we see that nothing happened. So this is an example of no movement, because Smith Larry is already sorted relative to Smith John. And then if you want to copy down how I inserted that, I'll post it, or I can just leave it up on the board during the break, you can add it in. You can look at the other 3 rounds, but the same thing will happen. Phelps is going to need to go ahead of Smith, and Riley, so it's going to be a triple move. So it should be a triple move on the next one that we'll do this. So we see that Phelps is here relative to Smith, and then next round we see so this was that round. But we're not seeing Phelps. That's weird. Well, there's something that's making it look like this, but you can see on the next one it's going correctly. Let's just see the back up. So we got the move where Getz was moved was. So Getz was moved during. Getz is moved from this round to the next round. So that's Getz. So Getz is sorted. So now this round, so this is just showing that Getz was sorted. So this is showing Getz was sorted. So now this round, it's actually sorting Larry and John Smith, even though they don't have to move. So I think that's the issue. So next round, we won't see any change. So Larry and John Smith are now sorted, but they weren't already, so nothing happened. So now Phelps has to be sorted relative to So now Phelps, we know this goes here. So Phelps sort, we would have to move Phelps here, Phelps there, Phelps there. So Phelps is 3 moves at once. So when Getz was sorted, it did 2 moves at once. When Phelps was sorted, it did 3 moves at once because of the wide loop operation. So again, insertion sort does more moves per round than selection sort because of the wide loop. The selection sort only has a 4 loop, which can only do 1 operation per round. So I'll leave the extra code up on the board while we go over it. I'll just highlight each one and then. So it's just this. I'll also post it, but I'll put it there in case you try to type it in. So it's just that code. If you put it after position and before the while loop, that will do what we just saw. So we'll do questions afterward, but so remember, like where it said, where it did 3 moves, that would be like 3n. So it would be like n times 3n, it would be like 3n squared. And if selection sort is just n squared, they're both the same because you don't count the scalar in front of the n. So n squared and even 1,000 n squared, they're both the same algorithm. So that's why these are both the same, even if there are more moves per interval. And if you came in a little later, I changed the due date for the homework to Friday night. Yeah, Friday night. Oh, and also, I think if you didn't get your test back, please come up and get it. So we're going to keep carrying them. So let's put them up here. The regrade is like circle with a check mark, so you'll know what it is. Most people got everything. A few people missed a few points, but most people did significant amount. I think everybody did significant amount. A few people didn't get all. So I want to show you
She said
how
later.
arrays are different.
Oh.
In that if you ever
Wow.
want to
Encoding
copy an
overloaded.
array, it's something that you probably
Oh.
haven't done yet. Or if you have,
Yeah, it's overloaded.
You can go to Rec Park or
121.
yeah, it's true.
So let's just see what the most
I played Z.
efficient
Outside. Don't know.
or base. Base. So we got here's selection sort, here's insertion sort. So the worst case scenario, which is the one that you always report, like if you come up with a new sorting algorithm, you don't say, oh, this is big omega, because that would be extremely good. But that's the best case. Like it's already sorted, so then your sorting algorithm runs it. It just has to check everything. So you never really report the best. Maybe the average, but usually say what the worst one is. Don't worry about space complexity. That means like space on the disk, but that's usually not.
What is this variable before
So
what is this little variable before the parentheses? Is it
this one is omega.
omega?
So omega is like big O is less than or equal to, omega is greater than. So omega is not usually used, but we'll mention it later, or you'll hear about it in other class. But big O is the most used. So n is big O of n squared. N is less than or equal to n squared. So insertion sort and selection sort are n squared. So the best one is
Sort. Oh no.
log n. No,
It's
no,
worse.
n log n. So notice that there are 4 of them that are n log n. So cube sort, which I don't know. Tim sort, that might be time sort, it's a spelling error. Cube sort and merge sort are the most common ones that you'll see in the textbook. So we'll just at least look at what merge sort looks like, and you'll see that the faster they are, the less easy they are to understand first time you look at them, because they tend to be more complex to think about, and they're fast. So
Wait.
the easiest one, let me see if there's one even worse than these two.
Yeah.
No, there's not. Well, actually, sorry. So radix sort, so where it says nk, like that's really the same as n squared, because that's like 1 times another, so it's, even though there's another variable name, it's like n times n. But n plus k, I'll look at that before next class, we could possibly look at it. That one is pretty fast, if it's real. But n log n is between n and n squared. So we have n linear, n squared, which is quadratic. N log n is between them. So log n itself is before n, but no sorting algorithm is log n. So n log n, let's just take a peek at merge sort. And then I'll just say my little thing about arrays in case you can any array copying some of the programming with the teachers. So essentially merge sort is divide and conquer, like you split the list in 2 and then you split both those lists and keep splitting them and then you combine it. So let's see if Wikipedia. So I'm going to have a graphic of it, which is probably really long. Well, this isn't animated, but we'll do it. Okay, so this is merge. So this is the one that is n log n, which is significantly faster than n squared. So the list starts out as that, and then it's split. If it's an odd numbered list, then one of the lists has one element more than the other. If it's even, it's just down the middle. So this is just the first half of the list, that's the back half of the list. And then this list is split, and then this list is split. Then they keep being split, and then each of the smallest lists are ordered, and then they are recombined, and then ordered again. So notice that we just look at the one that's 4 long. So the beginning of the list goes 38, 27, 43, 3. So then this list is cracked in half. So then 27 and 38 are sorted relative to each other. 43 and 3 are sorted. And then that is combined and then sorted relative to the rest of the members. So even if it looks like this is not faster than doing the selection sort, say it is. So then this list is sorted, and then the other list comes out sorted, and then they're combined and then sorted here. So the intricacy of how the extra sorting happens, we won't mention. Stick with insertion sort and selection sort for now, but this is n log n, so it is faster. And this is under the rubric of dividing. Divide, conquer each sublist, and then combine them back together.
If we know that some algorithms have speed of 1 plus k, why would just don't use them all the time? For example,
No
counting.
sorting algorithm is faster than n log n, that I know.
What about n
unless
plus
it's-
k?
What's that?
What about n plus k?
What is it though?
N plus k. The counting sort.
I have to look at that because I've never heard of counting sort. So I want to look because as far as I knew, n log n was best. But we can take a look right now for a minute. Let's just say. Let's see. There's array of elements, sorts of array. Sorting
Merge sort is like around 29 seconds.
Yeah.
And counter sort is blue is around.
Just trying to see let's just see what it says. So use the fact that the n elements are in a limited range. So it does have, there does seem to be something to it, because it says, use the fact that the n elements are in a limited range. So let's at least see what that means, because it means that there's a hinge. You know, like, counting sort is the best, but, so let's see if there's a but. If you ever want to look for good answer, I clicked on the C cell for MIT, that's the probably the best place to get an answer. It's usually after Stack Overflow, but just after. So let's just see about this limited range thing. It doesn't tell us. Let's just see. Counting sort. Yeah, it takes in a range, so it's not universal. You have to give it a range of integers. So you'd have to like pre-game it, say here's a range, which isn't a lot, but with radix sort, you saw below counting sort, that's universal, bird sort is universal, so counting sort, I guess the caveat is you have to tell it a range, which I guess is somehow that using that it speeds it up a bit, but it is an impressive speed at plus k, but I'll look at it more before next time and we can compare it to merge sort and see what n plus k means with respect to and log n. So it does look fast, but it's got this limit, like this little star thing. Okay, so this thing about arrays, if you ever are doing any printing something out, or you just want to like keep a copy of your array, there's something to mention. Okay, so say we have int x equals p, and int y equals x, and then we said so let's look at that. X. Okay, so when we have a primitive, if you assign value of x to y, y is also going to be 8. And then if we reassign x the value of 9, y is going to keep its old value of 8 because they're not good. So we'll be getting to something about raises. So we've got, both of them have a value of 8, and then when we print out them again, x has a new value, y still has the old value of 8 because y received a copy of the number 8 into its own memory slot.
What would happen if they were wrapper plus?
Well, that's not, the point is that with primitives won't happen, and with an object, you have to account for it. So a wrapper class, you can still get around it, but you have to use a clonable, which is what you have to do with arrays also. So the point of this is going to be, so if we have int integer array a1 equals 1, 2, 3, 4. 4. And then also the int b1 equals a1. And then we said to print out both arrays. Array printer. Okay, so we got the array A1 that has 1, 2, 3, 4, and the array B1 that has, well, supposedly it's going to have what A1 is. So you can do the same thing with primitives that you can do, with objects. You make an object A and an object B, and you say B, because we know that B is a reference variable to A. So we're going to show that something possibly unexpected happens with this. So we'll print out both. So we see that. Let me get rid of the first two. So we can see it. Okay, so they both have the same thing because we said B1 equals A1. But now if we go down here and do a position 1 equals 99. Okay, so if we do that, so that we're taking 99 and putting it where the 2 is. Let's see if it sticks to both, or if it just sticks to 1, and put C in the back. So let's just print it. After we do A1, position 1 in A1. So we get okay, so we get 1 and so it happens to both. So this is because arrays in Java are objects. So it's not really mentioned for whatever reason, I have no idea. But arrays are objects. So in order to change an array, you need to clone it. So cloning hasn't been discussed, but if you happen to ever want to, you're doing one of these sorting algorithms and you're like, oh, I just want to save a copy of the array, so you say B1 equals A1, you're not saving a copy, you're just pointing at the other one. So in order to copy it, you have to clone the array element by element. Using the method clone, and then you have to implement the clone function. So I'll make up a program that does that and post it and then just show it at the beginning of the next class, but you can't just do that because you'll simply be changing one place. And if you do the same thing, like if I change that to B1 equals 99, the same thing will happen. It changes both. Because B1 and A1 are both pointing at the same array. So arrays are objects. So it's just something to be aware of in Java in general. So when you want to do that, I'll put up a program. There'll be something like a for loop that you have to clone it element by element. But in order to do that, you also have to have your program implement the clonability phase. So it's just something to know. Some books say it, some books don't. And the same thing with objects. If you ever want to make a copy of an object, object A equals something and object B equals A. That will make a reference, as we know. If you want to make a real copy of object B, you can, but you have to use clone. So you'll at least see how it's used with arrays. And then it will be talked about more in 241 and other classes. But arrays are objects. They're not primitives. Even though they can hold primitives, as we know they can hold strings, they can hold anything. Arrays are objects themselves. So I'll put that up on Blackboard under documents and send it out. It'll just be for your information. So the assignment that was due Tuesday is we scheduled for Friday night. If you jammed up and you can't, just don't worry about it. Get it done when you can. Try to keep it within range so you're knowing what you need to know as we move along this semester. So so next time we'll look at searching for binary search. We didn't get a chance to do that. So try to understand insertion sort and selection sort. If you have any question on either, you can ask for next time. I'll also post up Blackboard the extra version of sorting where I'll put it in the place where it will print out the array each time. And I'll change it so it prints out the array on one line, so it's easier to read, like shorter, read it in a shorter space. I'll do that for both selection sort and insertion sort in the comparable and also in the primitive. I'll make a primitive version of insertion sort as well, so they can look at it without comparable. And it will just be a list of numbers. Although remember, for these we were considering capital B at number 1. S would be higher than B because of the S 2 and 4. So that's it. I'll also post up my little object separate program if you want to look at it. If you want to work on it too, I would be really happy to do that. I'm trying to rebuild the comparable interface. That's what it's meant. So we can receive any data and then give it somewhere else properly identified. So that's it. Thank you very much. If you didn't get your exam, please pick it up and grab it. I'll be in office hours from 2:45 to 6, probably 7. But 6, for sure. Nobody in here doesn't have their exam. There's like so many here. It's like, it's so I got you.
I'm
I work out only my Tuesdays. But it's still high.
Oh, really? Okay, yeah, I'm gonna just skip for the full console. That was cheaper. You want to try to do it?
Wait, it's over?
I think it's like yeah.
Are we doing a lab though?
From the home, we have series of conversions.
Is one of it's one of this thing. Oh damn. Bro, I'm tired.
So you can have series that has minus of the key power.